I'm not sure why they call them that, but that's, you'll see that terminology a lot. So more specifically to us, we can use the sine and the cos as a signal space. So let's use Si of k and Sq of k. Let's let them be. Let's let them use pulse amplitude modulation. So what's that? That's a fancy way of saying in the binary case, pulse amplitude modulation is polar NRZ basically. The signal is constant over its entire length. So e.g. in binary, I get polar NRZ. In 4-ary, I might have signals like +3, +1, -1, and -3. The point is that all of the samples in that signal are the same, but all I'm doing to differentiate signals from each other is multiplying those signals by some constant. So if I have a basis, if I have Si of k cos 2π fct plus Sq k sine 2π fct, then what I can do is I can say, let's let the basis in this space, we've already said, is so the basis signal is this. It's the constant signal up to NB, where the amplitude of each of these is 1 over NB, whatever root NB. What I'm going to do over here, so this looks something like when we were talking about a two-dimensional signal space. What this looks like is sort of like alpha I Sx of k, excuse me, alpha I Sx vector plus beta I Sy vector. So these signals are going to be like this. They're going to take various amplitudes, maybe +1, -1, maybe +1, +3, -1, -3, something like that. So what I can do is I can sort of describe this in the following way. I can say alpha I, call this the basis signal S of k for pulse amplitude modulation. Yes?
This cos twice pi of ct, does it have to be discrete time?
Oh, I'm sorry, yeah, that should be FDK. So alpha I times the basis signal, alpha I sk cos 2 pi f dk plus beta I at sk sine 2 pi f dk. So now it's as though, so think of it this way. If I just have alpha I sk, then what do I have? Really what I have is a one-dimensional signal space. So I can send a bit, whatever I like over here. I can send any Emery signal, whatever I like here. On this side, beta I sk, that's a different one-dimensional signal space. I can send an Emery signal over here. In fact, by the argument that I just made, I can send this signal and that signal at the same time and get both alpha I, get both the message conveyed by alpha I and beta I simultaneously. So we can further interpret this in signal space. So look at this. What I can do is I can collect these and call these basis vectors. They're not yet orthonormal though. That's the problem. So let's do our orthonormalization. So I'm going to say our first vector is this. It's S of sk cos 2 pi f dk. So let's call that. What I want to do is I basically want to take sk cos 2 pi f dk. And I want to divide that by the norm of itself. So remember with the first vector, if I pick this as my first vector, all that I have to do there's only one vector so far, so all I have to do to orthonormalize that is normalize it. In other words, make sure its length is 1. I'm abusing my notation a bit here. This should represent a vector with k elements, with nb elements, where each element from 1 to nb is given by plugging in that value for k. What is this? The norm of sk cos 2 pi f dk is equal to, well, for one thing, that squared is equal to the sum from I from k equals 1 to nb, there's nb elements here, of sk squared cos squared 2 pi f dk. Which is equal to, okay, what is sk for all k from 1 to nb? It's 1 over root nb. So that squared is 1 over nb times the sum from k equals 1 to nb. Cos squared 2 pi f dk, we've already established, is 1/2 plus 1/2 cos 2 pi 2 f dk. So I'm going to hand wave here. First I'm going to assume that that fd is an integer multiple